Hello and welcome. Today, we're diving into the world of digital elevation models, or DEMs. What are they? Essentially, DEMs are digital maps of the Earth's bumps and valleys, its topography. They are fundamental tools in understanding our planet's surface and are becoming increasingly vital across many fields. Think of a DEM as the foundational layer for countless applications, from planning where to build a road to figuring out where floodwaters might go. The way we create these crucial datasets has evolved dramatically. One key method is photogrammetry. This uses overlapping pictures taken from different angles to calculate elevation. We see this with aerial or satellite images, where sophisticated software processes stereo pairs to build 3D models. More recently, drones or UAVs equipped with cameras use a technique called structure from motion. By flying over an area and taking many overlapping photos, SFM algorithms can reconstruct incredibly detailed, high-resolution 3D surfaces, making it cost-effective for smaller projects. Another major player is LiDAR, which stands for Light Detection and Ranging. LiDAR systems shoot out laser pulses and measure the time it takes for the light to bounce back. Airborne LiDAR, mounted on planes, gives highly accurate data, even seeing through vegetation to map the bare ground, often considered the gold standard. There's also terrestrial LiDAR for detailed ground-level mapping, and even spaceborne LiDAR, like ICESat-2, providing precise elevation points globally, helping to calibrate other DEMs. Then there's radar interferometry, or InSAR. This uses the phase difference between two radar images, often from satellites like Tandem-X or Sentinel-1, taken from slightly different viewpoints. Its big advantage is working day or night, regardless of clouds, making it great for large area mapping. We also use GNSS surveys, think super accurate GPS. Techniques like RTK provide precise elevation points on the ground. These points are vital for calibrating other methods or can be used directly to create models for small areas. But increasingly, the best results come from data fusion. This involves combining data from multiple sources. For example, improving older global DEMs by integrating precise points from ICESat-2 or using machine learning to correct errors, especially in complex areas like cities or mountains. Creating DEMs is only half the story. How we analyze them has also advanced. We now have DEMs with much higher resolution, down to the meter or even sub-meter level, capturing fine details needed for urban planning or precision farming. Vertical accuracy is key for sensitive tasks like flood modeling. Beyond just slope and aspect, we now perform complex geomorphometric analysis. This involves deriving parameters like curvature or topographic wetness indices, helping us understand erosion, water flow, and even where certain habitats might exist. DEMs are indispensable for hydrological modeling. They allow us to map out watersheds, predict stream networks, calculate flow paths, and model floods, crucial for managing water resources and assessing risks. Modern software also enables immersive 3D visualization, letting us combine DEMs with other data, like satellite images or building plans for better understanding and communication. And artificial intelligence is playing a bigger role, automatically detecting features like landslides, improving DEM accuracy, and enhancing predictive models based on terrain. The applications for DEMs are incredibly diverse. They're used in infrastructure planning for roads and pipelines, site selection, and calculating earthwork. Urban planners use them to visualize development and manage expansion. Hydrologists rely on them for flood mapping and watershed management. Environmental scientists use DEMs to model erosion, map habitats, assess solar potential, monitor glaciers, and understand coastal changes. They're vital in natural resource management like precision agriculture and forestry. DEMs help in disaster management by mapping hazards like floods and landslides. Archaeologists can even find subtle, ancient man-made features hidden by time or vegetation. And of course, they are fundamental for cartography, creating the topographic maps and 3D views we often see. In conclusion, as the technologies for generating DEMs, from UAVs to satellites to data fusion, continue to improve, and our methods for analyzing them become more sophisticated, digital elevation models will remain absolutely critical. They provide a digital foundation for understanding, managing, and protecting our planet's surface. Thanks for tuning in.